Hello, welcome back to our series of current electricity. This is lesson 3 A-level physics prepared by Joseph Mayanja. In our previous lesson, we discussed the mechanism of electrical conduction, and the average drift velocity of the conduction electrons plus the heating effect of current, where we said that when a PD is applied across the wire, the conduction electrons usually gain kinetic energy from the applied PD, because it is this applied PD that accelerates these electrons across the conductor. As these electrons drift along the wire in the direction which is always opposite the applied field, they collide with the ions and lose their kinetic energy to the ions. These ions also vibrate with increased amplitudes. As a result, temperature of the wire increases due to the collision and friction. Before we get into today's topic, we want to explain how the drift velocity of the free electrons in a metal conductor carrying a steady current changes when the PD between the ends of the conductor is increased, then too the temperature of the conductor increases, but the current remains unchanged. When the PD between the ends of the conductor is increased, the drift velocity increases as the higher PD would accelerate the free electrons to a higher velocity. 2. We want to understand how the drift velocity changes when the temperature of the conductor increases, but then the current remains unchanged. We know that the drift velocity decreases as the temperature increases. At a higher temperature, the ions in the metal lattice vibrate with greater amplitude and the mean free path reduces, because as the ions vibrate with a greater amplitude, they block the passage of these free electrons. Therefore, the mean free path decreases and the free electrons are unable to accelerate to a higher velocity. This results in an increase of resistance to flow of current. Therefore, the current remains unchanged. Now, since we are talking about conduction, it is very important that we talk about conductivity of the material, and it is denoted by sigma. It is a Greek letter. Conductivity of the material is just the reciprocal of its resistivity, and it is noted by sigma, and this is the relationship that relates conductivity of the material and its resistivity. Resistivity of the material, like we shall see later in the chapter, is just the electrical resistance across the opposite faces of a 1 meter cube of a material. We are going to define that later and understand what resistivity is all about. And at this point, the SI unit of conductivity is per ohm per meter, and it simply comes from this, because we know that the SI unit of resistivity is ohm meter. But since it is a reciprocal, then this becomes per ohm per meter. And for all those people who deal with material science, before you use a material as a conductor, you must understand or know its conductivity. Because for you to be able to use material whose efficiency is almost 100%, you must know its conductivity. At this point, we need to talk about the famous relationship, a law that is very fundamental when it comes to all calculations of electricity as a chapter, and that is the Ohm's law. It is just a relationship that relates the PD, the current, and the resistance of a material. Ohm's law was discovered by a famous scientist called Simon Ohm, and he stated Ohm's law and said that it states that the current flowing through a conductor is proportional to the potential difference across its ends, provided the temperature and other physical conditions remain constant. Physical conditions like the area of the conductor. We can also talk about the length of the conductor. Simon Ohm proved that the current flowing through across the conductor is usually proportional to the potential difference across its ends. We know that potential difference is just the work done by 1 coulomb of charge to flow across the ends of the conductor. So for him, he suggests that the work done is proportional to the rate at which electrons flow across the conductor, because that is current. We know that current is just the rate of flow of electrons. So when you have a higher rate of flow of electrons, then you have a lot of work done. That is the potential difference across the ends of the conductor. So from that law, the potential difference, which is PdV, is directly proportional to the current at constant temperature. We must keep the temperature constant. In the following lessons, we shall see why when you increase the temperature, really everything changes when it comes to current and the potential difference. So we must keep the temperature constant. Therefore, to remove the proportionality sign, Simon Ohm introduced a constant, and that constant is what we call the resistance. So he came up with this famous relationship, V is equal to IR, and it is a very fundamental relationship in whatever procedures or in whatever calculations that you are going to encounter in electricity. At some point you are required to know this relationship, and it simply comes from Ohm's law. R is the resistance and V is just the PD and I is the current. To verify Ohm's law, Simon Ohm came up with this circuit, and in this circuit we have the cell, then we have our switch S, and then this is the rheostat. We emphasize and we say that the rheostat is just that variable resistor. Then we have the voltmeter, then the ammeter, and then another external load. This is also another resistor. The importance of an ammeter is to measure the current. All the current readings are going to be taken from the ammeter, and then the PD readings are supposed to be read from the voltmeter. This is our setup that is going to help us verify Ohm's law. These are our cells. The two cells are in parallel. Then this is our ammeter. Like you can see, the ammeter has 3 terminals: the negative terminal, the 1 ampere terminal, and the 3 ampere terminal. And the ammeter is arranged in series with the current source. Then we have our rheostat. You can see the rheostat is set at a 0 mark. It is a 10 ohm rheostat. Then we have a voltmeter, and remember we said the voltmeter is used to measure PD, and it is arranged in parallel with the 1 ohm resistor. Then we have our switch, and this is used to either complete the circuit or break the circuit, the flow of current. You can see that when the switch is closed, you can see the ammeter reading. You can see the ammeter reading plus the voltmeter reading. Voltmeter reading there is 1, and the ammeter reading is 0.5 when the rheostat is set at 0. Remember, in this setup, in this procedure, what you have to do is you set the rheostat to a certain value of resistance. The importance of a rheostat is to either increase the resistance in the circuit or reduce the resistance in the circuit. So when you set it to a suitable value there, let us see what happens when you close the switch. You can see that now the ammeter reading drops to around 0.18, simply because you have increased the resistance in the circuit. What happens to the PD? You can see that even the PD drops here. Initially the PD was 1, but now the PD has dropped to 0.24, around there. It simply implies that when you increase the resistance, the current is directly proportional to the PD, the voltage. Let us take another step, another set of results. Increasing the resistance in the circuit. The switch is closed. You can now see the value of the current, the ammeter reading. The ammeter reading drops. So is the voltmeter reading. And that one simply verifies Ohm's law.
Here are the steps that we go through in order to verify Ohm's law. So we are saying the apparatus is arranged as shown. The switch S is closed. The rheostat is adjusted so that the ammeter A and the voltmeter V read a suitable value of I and V respectively. After that, the ammeter reading I and the voltmeter reading V are noted and recorded in a suitable table. And the table is I in amperes and V in volts. The procedure above are repeated to obtain several values of I and V. What you actually do, continue varying the resistance. When you vary the resistance, you are either increasing the resistance in the circuit, and when you increase the resistance in the circuit, you are reducing the current. And when you reduce the resistance in the circuit, you are increasing the current. When you do so, take the suitable readings of I and V. Then thereafter, tabulate the results in a suitable table, and a graph of V against I is plotted, and the graph looks like that. V on the vertical axis and I on the horizontal axis. As you can see, a graph is a straight line through an origin, and this verifies Ohm's law. It simply means that the current flowing through or across the ends of the conductor is directly proportional to the PD across its ends, provided the temperature and other physical factors are kept constant. Like any other laws, Ohm's law has limitations. It does not really apply to semiconductors and gases, because these ones, the current is not directly proportional to the PD. Sometimes when the current increases, the PD does not increase. It only obeys if physical conditions like temperature are kept constant. But sometimes the temperature of the material cannot be constant, because we know there are some conductors, the moment the temperature increases, the resistance will automatically have to increase. So this law only is obeyed if the physical conditions are kept constant. Now, there are some conductors that obey Ohm's law and there are some conductors that don't obey Ohm's law. Ohmic conductors are those ones which obey Ohm's law. It means that for them, when the current increases, the PD also increases, and when the current reduces, the PD also reduces, provided the temperature and other physical factors are kept constant. But there are also what we call the non-ohmic conductors, and those ones don't really obey Ohm's law. And when we plot the I against V between the ends of the conductor, the shape of the curve is known as the characteristic curve of the conductor. So we are going to sketch the characteristic curves of both the ohmic conductors and the non-ohmic conductors, and we see how they look like. The characteristic curve of the ohmic conductors, e.g. the metal and other conductors, looks like this. It is a straight line through the origin, simply showing that as the current flowing across the conductor is directly proportional to the PD. For the non-ohmic conductors, the characteristic curves are different. First, let us look at that one of a filament lamp. It takes that shape, and simply this one means that current is not directly proportional to the PD. It increases but not with a uniform slope. Secondly, we look at the characteristic curve of a junction diode. This one simply shows that as the current increases, the PD increases, but the two are not directly proportional. Let us also look at the electrolytes, e.g. the dilute sulfuric acid. It is also a non-ohmic conductor, and the graph takes that shape. It is not a straight line through the origin, and simply that shows that this is a non-ohmic conductor. There are other curves, the semi-diode and other non-ohmic conductors.